Chapter 4, Section 9 is about oxidation-reduction reactions. Another way to call those is redox. The best way to remember what goes on in oxidation reduction is through the saying, Leo the lion goes grr, or Leo says grr. For this, the Leo part, L-E-O, loses electrons oxidized. The grr part, G-E-R, gains electrons reduced. So Leo the lion says grr. In an oxidation-reduction reaction, electrons are transferred. This can be spontaneously, but it could also be non-spontaneous with the addition of something like electricity. Let's take a close-up look at an oxidation-reduction reaction. Here we have sodium, which is a solid, and when it reacts with chlorine gas, a vigorous reaction occurs and produces sodium chloride. Each sodium atom in this equation loses one electron. I'm going to go over the rules of assigning oxidation states, and that's all these little numbers over the top of the elements here. But sodium initially has an oxidation state of 0. It's not sharing an electron with anything, and it has not given an electron away. So its oxidation state starts at 0. After the reaction occurs, it has a charge of +1 because it's given an electron to chlorine. So one way to write that reaction out is by sodium going to sodium plus an electron. That is called a half reaction. The other half of that reaction involves chlorine. So here we have chlorine, and again, it initially starts out with an oxidation state of 0, but it gains an electron and turns into chlorine with a -1 charge. Now, if we were to add both of these half reactions together, we would see that the electrons on either side cancel out. So you have one electron on the reactant side and one electron on the positive product side. All right, so again, I said Leo the lion goes grr, loses electrons means it's oxidized. In that example before, sodium goes from a 0 to +1, meaning it's lost an electron, so it's oxidized. Gains electrons reduced. Chlorine goes from an oxidation state of 0 to -1, so it's gained an electron and is reduced. There are some rules for assigning oxidation numbers. The first one is the oxidation number of any uncombined element is going to be 0. So like I said, sodium or chlorine by themselves has an oxidation state of 0. The oxidation number of a monoatomic ion is going to equal its charge. So if you have an ion in an equation, its oxidation state is going to equal its charge. So the example here is that any uncombined element here is 0. So the sodium is 0 and the chlorine is 0. The next rule is the oxidation number of oxygen in compounds is always -2. That is not the case if it's in a peroxide, but anything other than that, in general, oxygen is going to carry an oxidation state of -2. The oxidation state of hydrogen is usually +1. So here's an example. We have hydrogen as an oxidation state of +1, and oxygen is going to carry an oxidation state of -2. The next rule for assigning oxidation number is that the sum of the oxidation numbers in a compound is always going to be 0. So in the previous example, we have 2 hydrogens that carry a +1 charge, and oxygen which carries a -2 charge, and if we were to add those together, that would equal 0. Another example in calcium hydroxide, calcium has a +2 charge. Both of the oxygen carry a -2 charge, and the hydrogen carries a +1 charge. So the total charge of the OH here is -1, but there's 2 of them. Just put it out there. So calcium has +2. You've got 2 oxygens with a -2, and you've got 2 hydrogens with a +1. Add them all together, and that makes 0. The next rule is the sum of oxidation numbers in a polyatomic ion is equal to its charge. So an example, we know that the oxidation state of oxygen is -2. So we can set up something that looks like this. We have 3 oxygens, so 3 times -2 has got to equal the oxidation state of the whole polyatomic ion, which is -2. So what could X be in order to make this statement true? X has got to be 5. 5 plus 3 times -2, which is -6, is going to equal -1. Let's look at another one. Oxygen, again, is always -2. You have 4 of them, so that's a total charge of -8. The whole thing needs to carry a charge of -2, so X plus 4 times -2, or -8, has got to equal -2. So what could X be? Well, X has got to be 6. 6 plus a -8 is going to equal -2. There are ways that you can kind of simplify it. In general, not in general, but always, the sum of oxidation numbers in anything is going to be equal to its charge. So if it doesn't have a charge, the sum of oxidation numbers needs to equal 0. Hydrogen in a compound is always going to be +1, and oxygen, except for some peroxides in compounds, is going to be -2. It is important to note that not all reactions are actually redox reactions. So here is an example of one, and if we were to look closely, everything maintains the same oxidation number on either side of the equation. So you have silvers +1 on the reactants and the products. Chlorine is -1 on the reactants and the products, and so on. So there is no change in oxidation numbers, so that means it's not a redox reaction. Same thing with this next equation here. Sodium is +1 on the reactants and +1 on the products, and so on. So these are not oxidation reduction reactions. One thing that I do want to note, but we're not going to harp on, for some reason somebody decided to make this a little bit more complicated. So if something is being reduced, we call it the oxidizing agent, and if something is being oxidized, we call it the reducing agent. So for example, here sodium is going from 0 to +1, so it's lost an electron, it's oxidized. Another thing that we would say about it is that it is the reducing agent. Over here, chlorine going from 0 to -1, it's gained an electron, so it's reduced. We would call it also the oxidizing agent. There are some trends to note. Active metals, like in group 1, tend to lose electrons very easily, right? It kind of makes sense. There's one electron in its outer shell, so it's going to much more readily lose that electron. They are very easily oxidized. Active nonmetals tend to gain electrons easily, especially things in group 17. They are also easily reduced. There are some things to help you predict what's going to happen. So if you were to have MnO4 in an acidic solution, you know that it's going to produce manganese with a +2 charge and water. Let's go down to if you have any free halogens, for example, chlorine, it's going to produce that halide ion, so Cl-. I have this chart for you that goes through these. These are just charts, these are things to look at and think about that could help you predict what's going on in a redox reaction.